Hello. We will now continue with our study of solar system by discussing Mars. That is the next planet. Now you would say, but we didn't talk about the Earth. Well, our Earth is too dear for us. We have to spend a lot more time on it. So let's go and talk about the other planets. Then we will take up Earth separately. Well, Mars, I've given you some statistics. It's about 1.52 astronomical units away from the Sun. I hope you know what an astronomical unit is. Mars is the Roman god of war. You know, most of the names of these planets came from Roman civilization. Because of its red color, it is called the red planet. And you know that the name of the month March is actually derived from Mars. March, Mars. And it completes an orbit around the Sun in 687 Earth days, around 2 years of our time. Now, before this space exploration, Mars was considered to be the best candidate for life, extraterrestrial life. I'm sure you know about Martians in the movies, is that right? All kinds of grotesque looking animals were pictured as Martians. So life on Mars was considered to be a possibility before you knew much about Mars. Now, one of the reasons why life was considered to be a possibility on the Mars was there is some kind of an appearance of seasonal change, color changes. Well, so the apparent seasonal color changes led to speculation that conditions might support a bloom of Martian vegetation during warmer months and cause plant life to become dormant during colder periods. That was the speculation. But the speculation about life on Mars ended with photographs obtained from Mariner flybys in 1965 and 1969, providing evidence that the surface of Mars is like the surface of Moon. It has no canals or any vegetation. In 1971, Mariner 9 orbited Mars, photographing the entire surface and making extensive measurements of the atmospheric pressures and temperatures and so on. Now, the 6 common components of Martian atmosphere, there is a lot of carbon dioxide in Martian atmosphere and traces of nitrogen, argon, oxygen, water and so on. But the dominant atmospheric gas is carbon dioxide, which obviously makes it very hostile for life. The recorded temperature on Mars is a maximum of 20 degrees and a minimum of negative 140 degrees. Not very comfortable. The average atmospheric pressure is between 6.8 and 10.8 millibars. Now, our Earth's atmospheric pressure is about 1,000 millibars. That means the pressure on the surface of Mars is 1/100th of atmospheric pressure we have here. Very low atmospheric pressure. And some statistics about Mars, just like I gave you for Venus. It's nice to look at mean density is 3.94. Whereas for Venus it was 5.54. So Mercury is much less denser than Venus or Earth. So look at these statistics. You know, you can pause the video anytime. Although I go a little faster, you can pause it anytime and look at these details. The features of Martian surface. Now here's a picture of Martian surface. Now, one of the important characteristics are volcanic regions with inactive volcanoes, which is common for most terrestrial planets. So here we have a volcanic region. In the past, you can see the lava solidified into regions of rocky surfaces. Now, regions with systems of canyons, well, that is probably one of the reasons why people thought earlier on that there could be canals and things like that. There are deep canyons on Mars surfaces. That's right. There are complex layered canyons. And look at a very interesting feature of Martian surface. Regions of terraced plateau near the pole. You have a terraced plateau near the pole. An interesting characteristic there. Flat regions pitted with impact craters. You can see all over flat surfaces with impact craters. Mars has suffered large amounts of impacts from terrestrial objects. You can see those impact craters and also canal-like structures. Well, probably this is what led many people to believe that these are remnants of old canals. Dry channels suggesting water erosion, but really there is nothing like that existing on the surface of Mars. Viking 1 landed on the southern hemisphere on July 20th, 1976, and Viking 2 landed 45 days later and extensively toured those areas and sent us information. They did extensive analysis of the soil and evidence for metabolism. Well, metabolism will tell you evidence of life, respiration and other life processes, but no evidence of life in the past were uncovered. A very, very disappointing situation, is that right? Mars exploration rovers named Spirit and Opportunity. You remember reading about them, don't you? Now, were on Mars on January 4th and January 25th, 2004, and they are still roaming the surface of Mars. They found that Mars is made of basalt. What is basalt? Basalt is solidified lava, molten rock from the surface. Now, groundwater that is rich in sulfuric acid. Now, there is evidence that water, an essential ingredient of life, was present sometime in the past, but there is no evidence of water existing now. No evidence of life has been uncovered so far. Now, Mars has 2 moons, although Mars is a small planet. Now, they're called Phobos and Deimos. Now, this is Phobos. It is the largest of Mars' moons. It is an oblong-shaped moon measuring about 27 by 21 by 19 kilometers. Not very big. It orbits Mars with a period of 7.3 hours. All right. Now, this is the picture from Mariner 9 in 1971. Deimos is the other moon, which measures 15 times 12 times 11 kilometers, and that orbits Mars in 30.3 hours. So, the 2 moons of Mars, very interesting features. Let's now talk about Jupiter. Jupiter is the first giant gas planet. It is huge, and it is characterized by this belt-like structure it has. It's towards the center. Jupiter is the 5th planet from the Sun and is the largest one in the solar system. You remember, it's so huge compared with the Earth. More than 1,000 Earth could fit inside Jupiter, and it contains more than all the other planets combined. Jupiter contains more matter than all the other planets combined. In fact, well, Jupiter could have been a small star with a lot more masses. It is at a distance of 5 astronomical units from the Sun and takes 12 Earth years to go around the Sun once. The average density of Jupiter is a quarter of that of the Earth. It's about 1.2 gram per milliliter. It radiates twice the amount of energy that it receives. I told you some time ago that because the mass of Jupiter is so large, the gravitational contraction has created great big temperatures at its core, which then enables it to radiate visible light. That means it radiates more light than it receives. You see, all other planets radiates the amount of light they receive. In other words, the amount of light they radiate will be less than the amount they receive. But Jupiter radiates more energy than it receives. That means it generates its own energy due to the high temperature at the core. Now, but it cannot be a star because its mass is not sufficient. It has to be 80 times as massive to create nuclear fusion inside. In order that the temperature may reach that level, what is the temperature that is required for nuclear fusion? It's about 15 million degrees Celsius. In order to achieve that, Jupiter has to be 80 times as massive as it is now. Alright, so it's not going to become a star. Jupiter is a giant gas planet and its interior is mainly hydrogen and helium. Let's take a look at the interior of Jupiter. It has a solid rocky core. Inside of Jupiter is solid rocks. Look at that. This is the possible core that is rocky. And surrounding this is a thick layer of liquid hydrogen. There we have a thick layer of liquid hydrogen. It is compressed so tightly that it can conduct electricity. You see, electric current can flow through it because it is compressed so tightly. And for that reason, that hydrogen is called metallic hydrogen. Surrounding the core, you have a layer of hydrogen compressed so much that it can conduct electricity, is called metallic hydrogen. And above this layer, you have ordinary liquid hydrogen. So you got the rocky core, the metallic hydrogen, and then the ordinary liquid hydrogen. And outside this layer, you have Jupiter's atmosphere that contains hydrogen, helium, ammonia, and a mixture of ice and water. This is in essence what Jupiter is. Now the uppermost ammonia clouds mixed with sulfur and organic compounds are responsible for this bright feature of Jupiter. Bright orange, white and yellow bands you see on Jupiter is primarily due to the clouds of ammonia. In fact, most other planets also has this characteristic due to this gas. Now, bright hot gases are forced to the top where they cool, darken in color and sink back to the surface, forming convection currents. If you remember, we talked about convection currents. When gases are very hot, they are less dense, they rise up, where they radiate their energy, lose their energy, cool down, then sink back. This convection current is very much part of the making up of all planets. How about Jupiter's red spot? That is one of the most interesting characteristics of Jupiter. Jupiter's great red spot, located near the equator, is a very high pressure region, about 40,000 kilometers across, with higher and higher clouds. Now, it is a great big turbulence area, like a great big hurricane on the surface of the Earth. Now, this is a region of great turbulence. more powerful than the hurricanes on the earth, lasting for hundreds of years. You see, hurricanes on the surface of the earth are formed on water. They are fueled by hot, steamy water. But once they move on land, they lose their steam, they die out. And that's why hurricanes don't last a long time on the surface of the earth. But on Jupiter, there are no lands. That means it is continuously being fueled. So this hurricane or this powerful storm goes on and on and on for months on end. So the persistence of the great red spot is related to the fact that it never comes to land, as in the case of hurricanes on the surface of the earth, and that it is driven by Jupiter's internal heat. You know, the convection current actually brings up heat from inside, and that heat keeps driving this turbulence, keeping it going for months on end. And here's a picture of that great big turbulence, which is characterized as Jupiter's red spot. Now, how about Jupiter's satellites? Jupiter has 63 known satellites. There may be more we don't know. As of February 2004, Jupiter has 63 known satellites. Now, look at some of the names of some of the known ones. Io, Europa, Ganymede, Callisto, and these are called Galilean moons. They're called Galilean moons because they were detected using Galilean telescopes. And if you look at some of those, these are the pictures of a couple of those moons. Io has active volcanoes, and Europa is covered with thick layer of water and ice. Ganymede has valleys, ridges, folded mountains, and other evidence of active geological history. So all these are important features. How about Callisto? The most distant of Galilean moons is the most cratered object in the solar system. In fact, the number of hits probably it has received from terrestrial objects is so huge, it is absolutely cratered. Well, let's now talk about Saturn. Well, isn't the Saturn a beauty? Look at that beauty of Saturn. The rings of Saturn distinguishes itself. You can actually see the Saturn's rings on a small binocular. I have seen it. Saturn is the 6th planet from the Sun and is the 2nd largest in the solar system, with a diameter of 119,300 kilometers, and it is 9.5 astronomical unit from the Sun. Tell me, what is an astronomical unit? It is the distance of the Earth from the Sun, which is 150 million kilometers. All right. Now look at a closer look at the rings of Saturn. What is it made of? Anybody tell me what are the rings of Saturn made of? The rings actually consist of thousands of narrow bands of particles, some meters in diameter, big boulders, and some dust sized. So actually these rings are made up of dusts and boulder particles. They are debris just moving around Saturn. They look so beautiful because of the light scattered by them. Saturn has the lowest density of all planets, 0.7 of the density of water. Well, the density of water is 1 gram per milliliter. So you can imagine what the density of Saturn is. Saturn has 30 satellites, again 30 known satellites, including Titan, the only moon in the solar system with substantial atmosphere. Well, Titan is larger than the planet Mercury. Can you believe that? Saturn has a moon which is larger than planet Mercury. Now, Titan's atmosphere is mostly nitrogen with some hydrocarbons. Now, isn't it possible, by looking at this, you can say, hey, it may be possible that life could exist there, because Earth's atmosphere is mostly nitrogen. It's about 70% nitrogen. All right. NASA's Cassini spacecraft discovered potential liquid water on Enceladus, creating speculation that life forms could exist on this satellite. So you never know. We might discover something later on. Well, let's now go and talk about Uranus. Uranus is a beautiful blue planet. It's the 7th planet from the Sun and was discovered by William Herschel in 1781, not very long ago. And it is 19 astronomical units from the Sun, and it takes 84 years for Uranus to go around the Sun once. Now, radio signals from Uranus will take 2.5 hours. If you have a friend stationed in Uranus, and if you talk to him by your cell phone, it will take 2.5 hours for that signal to reach there, and 2.5 hours for it to come back. So you ask him, how are you, my friend, and go to sleep. When you come back, you can hear, yes, I'm fine. All right, 5 hours later. The atmosphere of Uranus is composed of 83% hydrogen, 15% helium, 2% methane, and small amounts of acetylene and other hydrocarbons. And methane in the upper atmosphere absorbs the red light. You see, methane has the characteristics of absorbing red light. So from visible light, if you take away a red light, the most prominent will be that blue. That's the reason why you got a bluish green tint for the planet Uranus. Well, how about Neptune? Neptune is another beautiful bluish planet. It has an equatorial diameter of 49,500 kilometers and can hold up to 60 Earths. It's a very huge planet. And Neptune orbits the Sun in 165 years. So it takes about 3 generations of humans for Neptune to go around once around the Sun. Well, the first 2/3 of Neptune is composed of a mixture of molten rock, water, liquid ammonia, and methane. The outer third is a mixture of heated gases comprised of hydrogen, helium, water, and methane. Now, methane, it is again the presence of methane that gives Neptune its characteristic blue color, because methane absorbs reddish colors, leaving us to believe that Neptune is blue. Now, actually, Neptune has rings like Saturn, but not very prominent. These rings are made up of dust particles thought to have been made by tiny meteorites smashing onto Neptune. So, as the meteorites were smashing in, the dust produced were going around Neptune, and that probably created the rings around Neptune. Well, I didn't want to leave Pluto alone, so I'll say a couple of words about Pluto. Pluto is a very small planet. It is smaller than our moon, is that right? And it was removed from the list of planets in 2006. It is now called a planetesimal. Its small size and its unusual eccentricity of the orbit where it crosses Neptune's orbit. Well, it is usually farther from the Sun than other 9 planets, but sometimes it crosses the orbit of Neptune. Alright, let's now come and talk about other objects in the solar system. We briefly discussed all the planets and the Earth, Moon. We will now look at other objects like the comets, asteroids, meteorites, and so on. What are comets? Well, you can see a bright looking comet there. Comets are small, fragile, irregularly shaped bodies composed of mixture of frozen gases, carbon dioxide, ammonia, methane, and so on, that orbit around the Sun in very highly eccentric orbit. Now, I want you to go and change this. It doesn't orbit around the Moon. Comets orbit around the Sun. So change that to the Sun. In very highly eccentric orbit. What does that mean, highly eccentric orbit? It means if this is the Sun here, a comet will come, approach the Sun and go away for a very long time. You see, it's very highly eccentric. The Sun is in that focus there. Okay. Let us now look at the components of comets. Comets develop a surrounding cloud of diffused materials, and we call it the coma, that usually grows in size and brightness. Now remember, these comets are small dirty balls of gas, mixture of ice and other dust particles. When they are very far from the Sun, they are actually a dirty ball. But as they come closer and closer to the Sun, they develop a coma. What's a coma? It's a cloud of diffuse materials which usually grows in size and brightness as the comet approaches the Sun. Why? Because the Sun's heat will evaporate materials on the comet, which will make it look bigger and, well, a small bright nucleus less than 10 kilometers in diameter. If you see, if that's a central dark region is the coma, the surrounding region is the nucleus, is visible in the middle of the coma. The coma and the nucleus together, if you take this one, the coma and the nucleus together is called the head of the comet. So as the comet comes closer and closer to the Sun, here's the Sun, the volatiles will evaporate, starting to build up the coma, the nucleus, and the head of the comet. When far from the Sun, the nucleus is very cold and its material is frozen solid within the nucleus, and it is referred to as a dirty iceberg. But as it comes closer and closer, when a comet approaches the Sun, within a few astronomical units, not very close, within a few astronomical units from the Sun, the surface of the nucleus begins to warm and the volatiles evaporate. What is a volatile? A volatile is a substance that becomes vapor very fast. You see, gasoline is volatile. When gasoline falls on your hand, it evaporates very fast. Now, ice is volatile. When sun's heat falls on it, it evaporates. The evaporated molecules boil off and carry small dust particles with it, and that is what forms the comet's coma. So the coma forms when the volatiles evaporate and carry with it dust particles and so on. When a coma develops, dust reflects more sunlight, and the gas in the coma absorbs ultraviolet radiations and begins to fluoresce. You see, fluorescence is the property of some substances by absorbing ultraviolet radiations, it will give off visible light. You know the fluorescent lamps we use at homes and offices? Inside that fluorescent lamp, there is a coating of zinc sulfide. And what is actually produced in the fluorescent lamp is ultraviolet radiations. The zinc sulfide will absorb the ultraviolet radiations and give off visible light. That property is called fluorescence. And the same happens in the comet. See, some of the particles are fluorescent. It absorbs the ultraviolet radiations from the sun and gives off visible light, giving the comet a bright, fiery appearance. Well, the sun's radiation pressure, you see, as the comet approaches the sun's radiation pressure and the solar wind, what does it do? Accelerates the materials away from the sun. So the radiation coming from the sun, like a strong wind, carry those materials, the volatiles that are evaporated with dust and so on, carried away in the form of a tail. So it depends on the size and mass of the material. Now, relatively massive dust tails. There are two types of tails that are developed in a comet. The relatively massive dust particles that are carried away by the radiation will bend because of their large mass. So this is the dust tail that bends away. Then there is another tail called the ion tail. The ion tails, the ions are very light. They are carried straight across. As the radiation pressure from the sun moves that way, the ion tails is just carried very straight across. Now the view of comet west, you can see those tails. This is the dust tail, that is the ion tail. Now each time a comet visits, you can see as the comet comes closer and closer to the sun, the volatiles evaporate and the sun's radiation carry the materials away. That means each time the comet visits, it loses part of its mass. So by the time it visits and goes away, it goes a thinner object, losing weight. It's a good way to do that. So eventually it will become just another rocky mass somewhere in the solar system. It will just get finished off. A time will come when that comet will never return. Now, Comet Halley is a very celebrated comet. In 1705, Edmund Halley predicted, using Newton's newly formulated laws of motion, that a comet that was visible in 1531, 1607, and 1682 would return. You see, he made calculations based on Newton's law and the orbital path of the comet, and he said this comet will return in 1758. Did it return? Yes, indeed. This is the Comet Halley. The comet did indeed return, and it was later named in his honor. So that's why that comet is now called Comet Halley. Alright? Comet Halley was visible in 1910 and again in 1986. And its next perihelion passage will be in 2062. And some of you can actually look forward to seeing the return of Comet Halley. What is Roche limit? Now, comets have very eccentric orbit. Now, that means when an object comes closer, you see, if this is the comet that comes close to the sun and then goes away. Now, if the orbit approaches the sun closer than what is required to keep the orbit, then the comet would probably crash into the sun. Now, the limit where the comet can stay in an orbit is actually called Roche limit. Now, comets have very eccentric orbit. The smallest distance at which a comet can orbit a celestial body such as the sun or a planet without being torn apart by the larger body's gravitational field is called Roche limit. In fact, the smallest distance it can stay away without getting caught violently into the gravitational field. Within the Roche limit, but above the Roche limit, it will stay in the orbit. If it crosses the Roche limit, it will break into pieces and crash inside. Well, this is an illustration of that. You can see this is the Roche limit. Above that, the comet will stay in orbit. If it goes within the Roche limit, it will break into pieces and collapse. Now, within the Roche limit, the mass's own gravity can no longer withstand the tidal forces of gravity, and the body then disintegrates into pieces. In fact, something like this happened to Jupiter, where a comet actually plunged into it. At least some of you remember that. It happened not long ago, and that comet was called Comet Shoemaker-Levy 9. The comet Shoemaker-Levy 9 was discovered by Eugene and Caroline Shoemaker and David Levy in 1993. Shortly after its discovery, it was determined to be in a highly elliptical path near Jupiter. It was going past Jupiter almost in a collision course. That means it came near Jupiter and crossed the Roche limit. In 1992, SL9, SL stands for Shoemaker-Levy, passed Jupiter within its Roche limit. What happened? It was broken into at least 21 separate fragments which were dispersed several million kilometers on its orbit. And between 16th July 1994 and 22nd July 1994, the fragments impacted the upper atmosphere of Jupiter. This comet actually crashed into Jupiter. Can you imagine the fate of the Earth if something like that happens? Will any life be left on the Earth? Well, you know, something like this has happened to Earth before. In fact, the dinosaurs disappeared long ago with something like this, either an asteroid crashing into the Earth or a comet like this crashing into Earth. Now, here I have the picture of those various fragments actually crashing into Jupiter. And this picture is actually taken by the Hubble Space Telescope. And this is where the comet is splitting into pieces, and you can see the impact where it impacted Jupiter. Can you see the big red spot on Jupiter? This is a picture taken by the Hubble Space Telescope. Beautiful picture. Okay, we will now talk about asteroids. What are asteroids? These big boulders, big masses that are actually wandering about within the space between Mars and Jupiter. On the first day of January 1801, Giuseppe Piazzi discovered an object which he first thought was a new comet. But after its orbit was better determined, it was clear that it was not a comet, but behaved more like a small planet. Piazzi named it Ceres, after the Sicilian goddess of grain. You know, because that planet looks so small, so he called it Ceres, the Sicilian goddess of grain, small. 3 other small bodies were discovered in the next few years, and now there are hundreds and thousands of them. By the end of the 19th century, there were several hundred of these discovered, and they were all named by the people who discovered them. Several 100,000 asteroids have been discovered and given provisional designations so far. And thousands more are discovered each year. So there's no end to this. There are 26 known asteroids that are larger than 200 kilometers in diameter. Can you believe if one of them lands on the Earth, what will be the fate of the Earth? Well, I don't want to frighten you, but it's a possibility, because look where we are. Now, this is Mars, that's Mars, and this is our beautiful Earth. And very often these asteroids cross and come in a collision course with the Earth. That is not unusual. There are many times that happen. Alright? Alright, the asteroids are found in the region between Mars and Jupiter. So you can see this is called the asteroid belt. The strong gravitational pull. Now, what keeps these asteroids there? Actually, you know, those asteroids would have become a planet but for the big influence of Jupiter. If Jupiter were not there, all these asteroids would have become a planet by colliding each other. Now, the strong gravitational pull of Jupiter prevented them from coming together to form a planet. See, now you can see most of them go after Jupiter because of the great big gravitational pull of Jupiter. There are two groups of these asteroids called the Trojan asteroids that lead and follow Jupiter. There is a group of Trojan asteroids that lead Jupiter. There is another group that follow Jupiter. So a third group of asteroids called the Apollo asteroids has orbits that cross the orbit of the Earth. You see, frightening. Those orbits, the orbits of those asteroids cross the orbit of the Earth, which means there is a possibility someday one of them can come and cross the Roche limit and crash into the Earth. It is possible that one of the asteroids could collide with the Earth. Let's now talk about meteors and meteorites. What are they? A meteor is a bright streak of light in the sky, a shooting star produced by the entry of a small meteoroid into the Earth's atmosphere. Here you can see a shooting star. That is a meteor. A meteor is a lump of material. When it enters the atmosphere, the friction, the heat burns them. You have a shooting star. Meteorites are bits of the solar system that have fallen on the Earth. If it doesn't get completely burnt off, it reaches the Earth, and we call that bits and pieces that reaches the Earth the meteorite. So I want you to distinguish the difference between a meteoroid, a meteorite, and so on. Here I have the picture of a meteorite that has been picked up by somebody. In fact, there are many times people do pick up these kind of stray objects coming through your roof. Well, if one of these falls on your roof, it'll make a big hole and land on your living room. Is that right? Now, most come from asteroids. A few probably come from comets. You see, these asteroids can actually hit each other, producing fragments, and these fragments would fly in all directions. And some of them, most of the meteorites actually are fragments from comets and asteroids. Now, in space, the remnants of comets and asteroids are called meteoroids. So those pieces that ultimately will become meteorites are called meteoroids. So I want you to know these terms. The streak of light and smoke that is produced in the sky is called a meteor. So when a meteoroid enters the Earth's atmosphere, the heat produced by friction burns them. And the bright moving object across the sky is a meteor. So meteoroids, before they become a meteor. And when a meteor falls on the surface of the Earth, it is called a meteorite. Yes, the falling star. A falling star is a meteor. A meteor shower occurs. You see, occasionally Earth moves through in space that contains a lot of dust particles. And that means these dust particles will be moving very fast in the Earth's atmosphere, and they all get burnt up. And that is what you see as the meteor shower occasionally. Larger ones fragment on entering the larger ones fragment or break into pieces when they enter the atmosphere, and still larger meteors explode in altitudes about 32 kilometers. Now, it is estimated that every 10 million years, all right, watch this carefully, every 10 million years, Earth will be hit by a very large meteor, devastating life over much of the planet. Well, you see, our lifespan is so small that I don't know if that is going to happen in our lifetime. But we have reason to worry about it because our civilization is in peril. You see, we depend so much on the mercy of all these natural phenomena. Do you remember we talked about the origin of the universe? What is the purpose of all this? Well, the only answer we have is, well, my God, tell me what this is all about. Tell me the meaning of my life. I depend so much on the mercy of the forces around me. Is that right? Yes. If a meteoroid survives the fiery trip, it strikes the Earth, and there you have a meteorite. We talked about that. Now, meteorites are classified into three basic groups: iron meteorites, stony meteorites, and of course stony iron meteorites. They're composed of, well, the name itself suggests, is that right? Most common meteorites are stony, composed of same materials that make up the rocks on the Earth, because they come from asteroids. Iron meteorites are about half as abundant as stony meteorites, and they consist of iron, nickel, and traces of other elements. Now, a newly fallen iron meteorite, don't think that they're going to really pierce through you. Well, it will. Well, it will be very hot, but not hot enough to cause a fire. So, it's a false idea if you think that it is a meteorite that fell in the forest that created a forest fire. It will be hot, but it will not create a fire. The stone meteorite will be just warm. Let's now spend a little time on the origin of the solar system. Well, you know how a star is born. The origin of the solar system is related to the birth of a star. Our sun is a star which originated in the planetary nebula, in that vast stretch of dust and gas, which, when got triggered, started a gravitational collapse. And let's see how, or at least construct a theory. See, don't think that whatever I'm saying is the truth. These are theories constructed by evidences that we think are true. So, what is the first stage of the formation of a star? A cloud of interstellar gas and dust is disturbed and collapses under its own gravity due to the shock wave from a nearby supernova. That is where everything starts. As the cloud collapses, it compresses and heats up the interior, is that right? And the center expands until equilibrium is reached. Well, this is the stage where a star is born. When the equilibrium is reached, you have a main sequence star. And here is the process happening. Now the gravitational collapse and the pressure from inside due to nuclear fusion in the nebula creating, of course, a star. Alright. Now the center compresses enough to become a protostar. Now you must understand, of all this dust and cloud, the center of that will contract to become a protostar. What is a protostar? A protostar is hot enough to emit light, but not hot enough to generate nuclear fusion. Alright, now for most of that gas flows inward. You can see it is a tremendous stretch of gas and dust. Most of that gas will flow inward, adding to the mass of the star. But the gas is rotating. You can see there will be a great big rotation generated, and as a result, it forms what is called an accretion disk around the star. The remaining dust and gas particles which did not really got into the center forms what is called an accretion disk, and the whole system is now rotating. Now here, the formation of an accretion disk. The center, this is where the center part becomes the star, and the remaining dust and debris and gas becomes part of the accretion disk. And here I have a picture of that. This is the accretion disk when you look at from one angle. You see, that is the center that is forming into a star, and the regions that surrounding it is made up of large quantities of dust and debris which did not really got caught into the center. So this disk is now in a continuous form of rotation. The collapsing, spinning nebula begins to flatten into a rotating pancake. You see, as it spins more and more, it flattens out. I'm sure you can understand that. The spinning causes the whole system to flatten out, with the star structure at the center and a big disk of dust and debris surrounding it in the form of a flat disk. You can see all of that material is now almost distributed in the same plane as the disk. Now in stage 5, the dust particles collide with each other. You see, as the disk rotates, the dust particles in the surrounding region will collide itself. Small dust particles collide to become big ones, form big boulders. The boulders will collide themselves, becoming bigger and bigger. You can see the transformation that is happening. The dust particles collide with each other and form into larger particles until they get into the size of boulders and small asteroids. Now here I have an illustration of this. Now this is the big disk that is surrounding the star, and you can see the dust particles colliding, becoming into boulders, into small asteroids, and this process continues in millions of years. There are collisions all over, and finally the gravity pulls in. As these particles grow in size, you see, they build up their own gravity, and they then pull in more materials. So their gravity pulls in more smaller particles, and the large objects accumulate all of the solid matter close to their own orbit, forming now what are called protoplanets. You see, the stage where planets begin to be formed. Now here you can see this is the accretion disk where you have large amount. This is the disk we are talking about, and this disk is in a continuous state of rotation, and the rotation has resulted in the random motion of these dust particles colliding against each other and generating these big boulders and asteroids, and their gravity then pulls in more materials. We got now what are called protoplanets. Well, things that could develop into planets. Now, if you take one of them, you can see this is an enlarged version of one of the protoplanets. And what does the protoplanet do? They also are subjected to gravitational collapse, pulling in matter and rotating. Alright. And seventh stage, about 1 million years after the nebula cooled. After about 1 million years after the nebula cooled, the star would generate very strong wind. Now the star has become a main sequence star, and the pressure from inside, the radiations coming from inside, generates a very strong solar wind. What happens? It sort of sweeps away most of the dust and debris that is left from forming of the protoplanet. It does a lot of cleaning up of the remaining space, so which would sweep away all of the gas that is left in the protoplanetary nebula. And in the next stage, if a protoplanet was large enough, its gravity will pull in the nebula gas. So as this gas is swept away by the solar wind, if you have a protoplanet which has a strong gravity, all that gas could be pulled in and it becomes part of that planet. So this is how planets begin to form. So then it would become a great big gas giant. So Jupiter is probably formed like that. All the dust, all the gas and dust that was blown away was probably caught in the gravitational field of Jupiter, which became a big red giant. Now, if not, it will remain a rocky or icy body. And our Earth and Venus and all the terrestrial planets remained rocky. And number 10, the planetesimals. Now, there are many objects that are now called the planetesimals, would slowly collide with each other. These protoplanets will slowly collide with each other and become more massive. Now here you got an illustration of that. These protoplanets could collide, and collision will be very fierce, and there you create bigger objects. And finally, after 10 to 100 million years, all these protoplanets will collide, become bigger planets. You will end up with, well, about 10 or 11 of these planets in stable orbits around the sun. And there we have a solar system. Look at this. We have now our beautiful solar system, which has got these planets. And it is almost stable now until something catastrophic happens. Is that right? And these planets and their surfaces may be heavily modified by the last big collision they experienced. For example, the last big collision the Earth experienced is resulted in the formation of the moon. Look at this. This is the last big collision the Earth suffered, and this is how the moon is created. Alright, we have now a picture of the solar system. We talked about the universe, we talked about the solar system. Have you answered the question, Where did the universe come from? Well, that is a complex question. Well, in our next lesson, starting in our next lesson, we will start looking at our Earth. Alright? Well, I will see you for that lesson later on.